Mr. Turtle, how many licks does it take to get to the Tootsie Roll center of a Tootsie Pop?
I never made it without biting. Ask Mr. Owl.
Mr. Owl, how many licks does it take to get to the Tootsie Roll center of a Tootsie Pop?
Let's find out. 1, 2, 3.
How many licks does it take to get to the Tootsie Roll center of a Tootsie Pop? The world may never know.
We don't know how many licks, but we do know how long. The project we chose involved related rates using a Tootsie Pop. It took approximately 8.5 minutes to reach the center of the Tootsie Pop.
Okay, so assuming that the Tootsie Pop is a perfect sphere, we can use the circumference formula of a sphere to find the radius. So in our case, our circumference was equal to 10. So in the equation, we replace c with 10 and solve for r. So we would divide by 2. Divide by 2, we get 5 equals pi times r, and then divide by pi, that cancels, divide by pi, and so our radius is equal to 5 over pi. Okay, so for step 2, we had to make a table with our data, and in 30-second intervals we would measure the circumference each time in order to find the radius at that time as well. So, for instance, at 8.5 minutes, when we actually got to the center of the Tootsie Pop, our circumference was 6.8. Okay? And just like in step 1, all you got to do is plug in 6.8 for C and solve for R. And so divide by 2, divide by 2, 3.4 equals pi times R, and then divide by pi. That cancels. And so our final circumference was, our final radius was 3.4 over pi. In step 3, we made a scatter plot on Excel using the values in the previous step over the time interval of 0 to 8.5 minutes. Okay, so in step 4, we're going to use our line of best fit we found, which is negative 0.0617x plus 1.5875 to find our overall dr/dt. And all you got to do is take the derivative of this function. So that gives us dr dt equals negative 0.0617. Okay, so for step 5, we had to make another table using the volume of a sphere to find the volume at each 30-second interval. So for an example on what you're supposed to do, we're going to use our final R value, which is R equals 3.4 divided by pi. And we're going to simply plug that into the equation. So V equals 4/3 pi times 3.4 divided by pi cubed. And when we multiply all that together, that is going to give us our answer, which is 5.310 centimeters cubed. Okay, so for step 7, we're going to calculate the rate of change of the volume over time of our Tootsie Roll Pop. So we're just going to take the derivative of the volume of a sphere, and this is going to be implicit differentiation. So we're going to have dv dt equals to 4/3. This is a constant along with pi, so we're just going to move them out, and we're going to take the derivative of this. So because it's implicit differentiation, we're also going to end up multiplying by dr dt. So this is like having x here. So this is going to be 3r squared now times dr dt. Then, once we simplify things, so 4/3 times 3, the 3's just cancel, so this can be simplified to dv dt is equal to 4 pi times r squared dr dt.
In step 9, we found the average value of the rate of change of the volume of the Tootsie Pop. We calculated this by adding all of the dv/dt values and dividing them by 18, which was how many measurements we took. The average value that we ended up getting was negative 1.162 centimeters per second. An interesting example that we found of related rates involved the older model of the iPod. So basically in the older model there was a touch sensitive wheel just like this one, and the faster that you moved the wheel, basically the faster the cursor would move on the screen.